All right, everyone, we are recording now. So, once again, everything I put up here, if you can't get it all written down or you don't feel like writing it down, you're just better at just listening, this all gets posted after class. We're going to talk about relations. It's a mathematical term, relations, and what it is just going to be a list of ordered pairs. So to make sure we're all on the same page with what an ordered pair is, we just need to remind ourselves that an ordered pair is two numbers in parentheses, separated by a comma, in the proper order. So that is what an ordered pair looks like, 2, -3. And it's okay, some of you are returning to math after a long time, or some of you just took a math class last semester, some of you maybe read ahead already, some of you just maybe naturally enjoy math more than other people. But a lot of us may have heard at one point or another that this is almost always what we call the x value, and this is what we call the y value. But remember, when you're giving an ordered pair, and this goes for taking exams or doing your online homework, when you're giving an ordered pair, there are a lot of things you need to make sure of. For instance, it's not the same thing when you write them in the wrong order. They're called ordered pairs for a reason, because it does mean something different if you write the order opposite. It means something different if you use brackets. Brackets actually mean something different in math than parentheses, so you can't use brackets. You do have to use parentheses. You do need the parentheses too, otherwise it's just a list of numbers and it's not an ordered pair. And then unfortunately, this is the one that I actually have to pinch people a lot on, and I hate doing this one, where they knew it was parentheses, but they forgot the second one. But you do need them both. You do need them both. So make sure when you give an ordered pair, two numbers in parentheses in the right order, separated by a comma. So now that we're reminded what an ordered pair is, a relation is just a list of these things. When we write a list in this class, we often put it inside a set of braces. So a relation would look something like this. Just a list of ordered pairs. Later we're going to graph one of these relations. We'll see what they look like when you graph them, but that's all you need for a relation. It's actually pretty easy to be a relation. You just write a bunch of ordered pairs and you've got one. And for each one of these ordered pairs, the first value is x and the second value is y. And that's it. 1, 4, 3, 6, and 2, 7. And sometimes with a relation, you can find the rule of how one goes from the first number to the second number. And other times it's just a list of ordered pairs. So don't try to figure out how these two numbers are related in each one of these things unless someone specifically asks you to figure that out. Because these I just wrote up here randomly. It's possible you might see one that looks like this. 1, 2, 2, 3, 9, 10. And that one we can look at, and if you study long enough, you'll see the rule. Oh, I see. Whatever Steve put in the first slot for the x value, he's adding one to get to the next one. In fact, this relation right here can be described by an equation where you'd write something like this. Y equals x plus 1. And if someone said, what do you mean? You just say you add 1 to x to get 1. But this one I have no idea what the rule is. I just picked a bunch of random numbers. So that's what a relation looks like. It might have, 50 numbers on the list. It might just have 2 numbers on the list. But we actually saw that, if you remember, in that first homework problem I was showing you. It said give the domain. We'll talk more about that in a minute, but I gave you a relation. This is not the only way you'll see a relation in this class. You might see them in a table. So sometimes someone says, I'm going to give you a table and call that a relation instead. So they might go like this. XY, -20, -10, 50, 25, 2, 1, I don't know, 8, 4, something like that. And you can probably spot the rule there. How do I get from x to y? What do I do? Cut it in half, divide by 2. That's a relation also. And one that you'll occasionally see when you're talking about relations is a mapping. We don't use this one very often. Yes, everyone, you are in the right place. This is college algebra. But I'm not sure if I ever really grew up with some things, so I made one here that was a bunch of Muppets and what color they are. And then you draw these arrows to show which one goes to which. If you're not familiar with the names Ernie, Bert, and Grover, they are Muppets from Sesame Street, and you can take my word that's what color they each are. So relation could be a list of ordered pairs like that, it could be this, or it could be this. And you could see how you could turn this right here into a bunch of ordered pairs, or this right here into a bunch of ordered pairs with words. I mean, if I wanted to take the time, I could write one that looks like this. Ernie, orange. And I could do that with the other names as well. And with this over here, I could say, you know, -20, -10. There's one of them, and I can list the rest of them. So maybe they're not presented as a list of ordered pairs, but they could easily be turned into a list of ordered pairs. Okay. All right, so what's something we need to know about relations? Well, it seems that relations, every ordered pair has a starting and an ending. We got the first values, and then we have the second values. So most of the time in a math class, the easiest way to describe those are as the x value and the y value. But maybe you're doing something like I did with the Muppets earlier, like that, and so you might just want to say the input and the output. Or another term you'll hear come up is the independent variable and the dependent variable. Independent, because I kind of pick it. I pick which Muppet I'm going to talk about, and then depending on which one I picked, that's the color I get. Or depending on which starting number I picked, I get a certain ending number. So independent and dependent. You'll actually see that in your homework, this vocab word, when you do that pre-work for 2-3. Most of the time you're doing pre-work before I teach it, but for the sake 2-3, you're going to be hearing some of it before you do the homework. And then the big words we're going to use a lot are domain and range. When someone starts talking about the domain, they're talking about all the starting values, all the inputs. When someone starts talking about the range, they're talking about all the ending values, all the outputs. These come up a lot in this class, especially domain. All right, so that's kind of one of the first things you're going to see is people hitting around about this domain and range when they give you a relation. They're going to say, hey, I've got a relation for you right here. Maybe something like 1, 2, 3, 7, -8, -20, 1, 7. And they want to know the domain. So since you were all awesome and came to class today, thank you for coming. You know that domain is asking for the x values, the input, the starting numbers. And so you write them down. And it marks you wrong. You're like, what gives? And it turns out when you're getting a domain, you don't want to repeat values if they get repeated. So we don't want to actually use this other one because we already wrote one. What's nice is it doesn't matter what order. So if you prefer to like go in ascending order rather than the order you see them, I just wrote them as I saw them going across. But someone else might say, boy, I think I'd rather write them from smallest to largest. That's going to give you full credit also. And then when you do your range, you just look at the second numbers. 2, 7, -20, another 7. Do I repeat 7? You can just shake your heads. No, don't repeat that. 2, 7, -20. These don't need to match up with these. It's just a list. You're making a, here's where they need to match up. Down here, they don't. Here, you're just making a list of the domain and a list of the range. All right, cool. So we can give the domain a range. One of the most critical functions we ask, or questions we ask about any of these relations, though, is this. Is the relation a function? And man, we're going to hear that word a lot in this class. It's going to come up over and over again. So this is not the part to kind of zone out and say, I don't think I care about functions. Because functions are a big deal. In fact, when I first learned about functions in math class, I think I like blinked, and then I was confused for the next 3 years. I had no idea what was happening. So this is an important part. Is the relation a function? Well, I guess if we're going to answer that question, we need to know what a function is. A function is a type of relation such that every element in the domain corresponds to a single element in the range. Now, if that looks too wordy to you, join the club. I'm going to explain what it means in a second. A function is a type of relation such that every element in the domain corresponds to a single element in the range. And we'll see exactly how to determine whether or not the relation you're looking at is a function or not. So, here's a really short relation that is not a function. Because if someone said, I'm thinking of the element 1 in the domain, what does that correspond to in the range? There's two answers to that question. It corresponds to both 3 and to 4. So this is not a function. Because in a function, you need it so every element in the domain corresponds to only a single element in the range, not 2 different ones or 3 different ones. Now this one's not very exciting because it's only 2 ordered pairs, so we're going to look at another example. I just wanted to give you that example right away. So if we look at another relation, I'll give you that there, okay. If we look at another relation, and it's easy to be a relation, you just need to be a bunch of ordered pairs. The thing that's not quite as easy to be is to be a function. I'm purposely going to write another ordered pair there in a second. That's why I left some room here. If you're writing down the notes, that's why I did that. Now, everyone look at this thing right here. And you look at the domain. The domain's going to be 1, 5, 7, and 10. But 1 goes with 4. Does it go with any other number? No. 5 goes with 6. Does 5 go with any other number? No. Does 7 go with any other number but 2? And 10 doesn't go with any number but 8. This is a function, everyone, because every element of the domain, 1, 5, 7, and 10, corresponds to a single element in the range. So as this sits right now, this group of ordered pairs is definitely a function. But I wonder if there's an ordered pair I could add to this to make it so it's not a function anymore. And yeah, I could. I could easily add an ordered pair to make it not a function. Now, I need to work a little bit at it because I can't just write anything I please here. But what do I need to do to make another ordered pair? What do I need to do? I need to make this ordered pair start with what? One of my numbers that I've already used in my domain. Brilliant. So could I start with 1, 5, 7, or 10? And then once I do that, I just need to make sure I don't repeat the exact same ordered pair I already did. So I'll mess this up if I put a 2 right here, because then I'm just repeating an ordered pair. I'm not giving a new y value to go with that x value. Everyone see that? So I just need some other y value. I can put any single number I want here except for 2, and I win. Done. Now it's not a function. Now it's not a function because 7 corresponds to both 2 and 100. And that's what we said. To be a function, you need it so every element in the domain, 1, 5, 7, 10, corresponds to a single element in the range, not more than 1. Function. Done. Oh, I'm sorry. When you put this on, not a function. Okay. Now, here's something that sometimes messes people up because they're like, I think I've got that, and then I write this. And then I ask people, is this a function or not? And a lot of people who are just learning this for the first time think that this might not be a function. Why would someone think this might not be a function?
2 3s.
Yeah, they see the 2 3s and they're like, Steve, you're repeating a 3. But then we need to remember that it's not a function if the x values repeat. So it turns out the x values 1, 2, and 6 don't repeat. So, this is a function because y values can repeat in a function. It is okay for the y values to repeat, just not the x values. So don't let that mess you up. Because you don't want to just think, oh, if it's a repeat, we're done. It's over. It's not a function. No. If the x values repeat, it's not a function. Whether or not a relation is a function you can give domain and range. It doesn't matter if it's a function or not. You can always make a list of all the first numbers and a list of all the second numbers. So don't think just because it's not a function doesn't mean it's worthless and we'll never see it again. No. There's plenty of things that aren't functions that are important in math. But functions are what we're focusing on right now. All right, so here's my hot tip. We'll make this in red because it's red hot. Hot tip of the day. Actually, I almost feel better if this would be like the hot tip of the day. Hot tip of the day. All right. Is a relation a function? This is a big question you're going to ask yourself in this class and in doing the homework. If no x values repeat, it is a function. If you have a repeated x value and two or more different y values, it is not a function. Once you get the hang of this, it is supposed to be a pretty quick procedure. Just kind of scanning your eyes over the x's and seeing if any of them repeat. I'm not saying you're all going to be the fastest at it right away, because that'd be a rude thing to say in a math class, but I will say once you get the hang of this, it's supposed to be pretty quick. Just like way back when someone told you to memorize your multiplication tables, maybe, and once you got the hang of it, it was quick. It was a pain in the neck to learn it. But once you remember that, you know, that 7 times 8 and that 9 times 6, those were the two that always messed me up. It wasn't so bad. All right, so everyone do this for me. Just on your own. Oops, sorry. Put the hot tip of the day back up there. First, we're going to decide if this is a function or not.
Yes.
You think yes? And is it as quick as going like this? 1, 2, 3, 6, no repeats. Is it that quick? Is it really that quick? Yeah. Someone might not think it's a function because they might see all those 6's in there. Might say there's no way there's a function with all those 6's in there. But you'll notice there's only one time I use a 6 for an x value, and the two over here are both y values, and it doesn't matter if we repeat y values. So this is a function. So everyone do me a favor. I want you to write down an ordered pair that you could add to this so it's still a function. And I want you to write down an ordered pair so it's not a function. So write down one that you could add so it's still a function, and then write down one that you could add so it's no longer a function. And once you get the hang of this, it is supposed to be fast. Maybe it's not fast today because it's new. Maybe it's not fast today because I write too quickly for you and you can't get all this copied down in order to do this. But once you get the hang of this, you will be able to do it quickly. And your first one's going to be fine as long as you started it with anything but 1, 2, 3, or 6. As long as you put some number here, and it didn't matter what you put in the second number, as long as you put some number here that wasn't 1, 2, 3, or 6, you won. And here, start with 1, 2, 3, or 6, and for your second value, don't repeat the exact ordered pair. In other words, if you wrote 1, don't write 5. If you wrote 3, don't write 6. So probably the easiest example I could do for this would be this. If I wanted to give my 2 correct answers, I would do this. 0, 0, start one with 0. And if I wanted to do this one, I would do 1, 2. Start with one, end with a different number. How many correct answers are there to each of these? Infinitely many. You could all have different answers and you could all be right. If you're freaking out that yours is wrong and you want to show it to me later, that's fine. All right. Let's move on here. Check this out. This is, haha. Everyone just produce a graph in your notes right now so you can follow. No, I'm just messing with you. But I'm going to draw a graph here. Because when we have a relation, and it's a list of ordered pairs, I don't know how you'd graph Ernie, Burton, Grover, but if it's a list of ordered pairs like this, I'm actually going to pause for a second here. Back to it. Once we have a relation, we can plot it over here on a coordinate system. So that's exactly what I'm going to do. So we know that it's xy, 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 xy. Maybe we're a little bit rusty at graphing, but we know. Go over 2, up 4. That gives me one of my ordered pairs. Backwards 6, up 3. That gives me another ordered pair. 5, 1. And 0, 2. Now, do we all agree that this, as it stands right now, is a function?
Yes.
No x values repeat, it's a function. We have a winner. And please respecting that my coordinate system only goes from -10 to 10 in each direction. Someone want to give me an ordered pair that will kill the function?
-6, 2.
-6, 2. I also heard 2, 6. Let's go 2, 6. I like that one. -6, 2 is a fine answer. That would also work. All right, so 2, 6. That just killed the function. Now 2, 6 doesn't have a problem with every ordered pair, it just has an ordered pair that starts the same way it does. The 2 ordered pairs that are causing this function to die are this one right here and this one right here. Because they both start with 2 and they end with 2 different numbers. That's what makes it not a function anymore. And those 2 points are on the graph right here, 2, 6 and 2, 4. And without jumping the gun too much, because I know some of you know exactly what I'm building up to on this, and that's cool, but without jumping the gun too much, for those of you who have not seen this before, what do we notice is the relationship between these 2 points? They're on the same what? Or they're on the same vertical line. One's right above the other, or the other's right below. But they're both on the same vertical line. And none of the other points are on a vertical line with any of the other points. Now, yes, of course, you could connect 2 dots if you wanted to, but none of the other 2 points are on the same vertical line. Does everyone agree with that? So the 2 points that cause a problem are on the same vertical line. All right. So these 2 points that kill the function are on the same vertical line. And that's going to be something that's going to help us a lot. And the reason that's going to help us a lot is because if I have a list of just 4 or even 10 ordered pairs to look at, I can pretty quickly make my way across that and make sure none of the x values repeat. But many of our relations, in fact, almost every relation we discuss in this class, many relations and graphs have an infinite number of ordered pairs. And of course, if there's an infinite number of ordered pairs, we can't check them all out one by one, looking at them, looking for a repeat in the X. We're going to need something faster. And it's really, really going to help us. This idea right here, that the two that spoil the whole function laid on the same vertical line. Class, right now I have 650 up here. It just turned to 650, so we'll come back at 7:01, and we'll do some more math. So when we left off, we said that many of our relations, whether they're a list of ordered pairs or a graph, they're going to have an infinite number of ordered pairs. So if we have an infinite number of ordered pairs, how can we check if the relation is a function? Well, often what happens is we often get an equation. We often get an equation. And an equation is actually how we're often going to see these relations given. And the reason that can be classified as a relation is because it can generate an infinite list of ordered pairs. Now, I'm not going to write down an infinite list of ordered pairs because that'd be silly and I couldn't do it. But this can create as many ordered pairs as you want just by picking an x value and getting a y value out. For instance, one of the ordered pairs on this is 1, 6. Another ordered pair on this is 2, 11. And I could plug 1, 2, 3, 4, 5, 6, 7. I don't even need to do positive numbers. I could do negative 18, negative 20. I could do fractions. I could do decimals. And I could create an infinite list of ordered pairs by multiplying my number by 5 and adding 1. So we can't possibly check all those ordered pairs to see, if that actually is a function. Or maybe we have a graph. Maybe we have a graph that looks like this, and we're looking at that and we're trying to decide, well, that's actually an infinite number of ordered pairs right there. They're just all so close to each other, it doesn't look like a bunch of points, but it's an infinite number of points. Because there's one here, and there's one here, and there's one in between them, and there's one in between those, and there's an infinite number of ordered pairs there. Just keeps going and going and going. So what do we do? Decide, is this a function? Well, the graph is easy if you understood what I was doing right before the break. And what were we doing right before the break? We were looking at this and deciding that the two ordered pairs that mucked it up for everyone were the two ordered pairs that laid on the same vertical line. And we can do that, we can look for that, even if it's not just a bunch of ordered pairs, even if it's like a curve. They're all so close to each other. So, class, check it out. Here's a graph with an infinite number of ordered pairs. Do you think that's a function? No, because even though I don't know the exact numbers for the ordered pair, can everyone see, and this is not the only place this happens, can everyone see that there's a couple ordered pairs here, actually 3 of them, that all lie on the same vertical line? Now, I don't know exactly what the x value is, and I don't know exactly what those y values are, but I do know this. Those 3 ordered pairs on that vertical line all have the same x value, and they all have different y values. Isn't that what we said destroys a function? So this right here is not a function because of the vertical line test. If it is possible to draw a vertical line and hit a graph at more than one point, then we say this. It fails the vertical line test and is not a function because it is possible to draw a vertical line and hit it more with one spot. Now someone might say to me, Steve, looks like a function to me, that vertical line only hits it once. Well, that's one vertical line. We need to see, is it possible for someone else, anyone, to draw a vertical line and hit it in more than one spot? And if they can do that, then this is not a function. Huh. You think that's a function?
Yes.
I think it is too. Because, we're not going to do this, but everyone could come up here and draw a vertical line. And even when the graph gets really steep, none of those vertical lines are going to hit the graph more than once. Does everyone see that? So what can we say? We can say this is a function, passes the vertical line test. Because you can't draw a line and hit it more than once. All right. So when you say something fails a vertical line test, that means it's not a function because you were able to hit more than one spot. And it doesn't need to be everywhere you hit more than one spot. Just one place can screw it up for everyone, just like these 2 points screwed it up for everyone. So, does this pass or fail the vertical line test, the first one here? Fails. If it fails, therefore, it is not a function. Fails, VLT. What do you mean it fails? See, it fails. Not a function. How about this line over here? Does this pass the vertical line test? Yeah, it sure does. Passes VLT. This right here is a function. In fact, we can make this statement right now. It's pretty cool. We can say this. Every line except vertical lines are functions. Every single line you ever draw in mathematics, and remember what line means, everyone. There's no such thing in math as a curvy line. A line is straight, always. If you want to say a curvy line, you actually just say a curve. So every line except a vertical line is a function. So, wait. Is a horizontal line a function? Yeah, absolutely. It passes the vertical line test. Doesn't matter how many vertical lines I draw. Everyone only hits it once. So this is a function. All right. Now, and this is my fault, not yours, I can get so deep into talking about functions, we can start thinking that functions are the only thing that matters. That if it's not a function, we hate it, it's garbage, we should get rid of it. That's not true. That's not true because a circle is very important in math and is not a function. We love circles in math. They're a very important mathematical shape, but it's not a function. So just because something's not a function doesn't mean it's garbage, but it turns out in this class, except for our last unit, which will be unit 4, we mainly focus on functions in this class. So for the most part, yes, we will be talking about functions most of the time. But there are things in math that are important that are not functions. All right, cool so far? All right, here's an important little detail. I'd like to spend some time on some of the details, because the book can teach you a lot, but it doesn't always get into these ideas. A hollow point on a graph is a missing point. And a vertical line does not hit a hollow point. You may have seen a graph at one point that had like a missing point on it, and they indicated that by just putting a little open circle instead of a solid circle. And then someone asks you, is this a function? And someone might say, well, this vertical line, no problem, this vertical line, no problem, this vertical line. However, well, wait a minute. How many times does this vertical line hit the graph?
Once.
Just once, because a hollow point doesn't count as a hit. So, this is a function. Hollow point doesn't count as a hit. Is that a function? Does a vertical line have to hit the graph? It doesn't have to hit the graph. It just can't hit it more than once for it to be a function. So this vertical line right here, everyone, how many times did that hit the graph? 0. Is that okay for a function? That's all right. You don't have to hit the graph with every vertical line. You don't have to. For instance, is this if I got rid of the red point, would this be a function?
Yes.
Even though there's tons of places I could draw a vertical line and not hit anything, right? The problem is if you hit it more than once. So hitting it 0 times, that does not mess us up. So this is absolutely a function. Well, I'm guessing this is a function because look, these vertical lines are only hitting it once, so that's probably a function, right? No, what do you mean no? I'm the math teacher. Well, it is possible to draw a vertical line that hits the graph more than once. So, fails vertical line test, not a function. I don't know what those ordered pairs are right there and there, but they both start with the same x value and end with different y values. Now graphs are fine because we can use the vertical line test, and most people do pretty well with the vertical line test once they get the hang of it. They just need to remember what it means when they hit it more than once or they don't hit it more than once. What can cause a problem is this question right here. Is the equation a function? If you're looking at an equation, is it a function? And you might think, well, here's the issue. An equation, I think Steve said, can pretty much generate an infinite number of ordered pairs. So we can't write down all the ordered pairs. And it's possible that I won't know how to graph it right away either. I do not know off the top of my head how to graph that thing. And I also don't want to graph it just to see if it's a function or not. That seems like a lot of work just to answer a yes or no question. I'd almost rather get it wrong on the math homework, and then if it tells me I'm wrong, pick the other option. Well, how do we figure this out? Well, here's what we already know. A line, not vertical, is a function. So that takes care of some equations right off the bat, because those are both equations for lines. Different forms of equations for lines, but those are both lines. This one, a lot of us know this one, this is called slope-intercept form. Little mx plus b action there. Depending on where you took college algebra, this might be called standard form or general form. A lot of times the way you drew this one was you put in a 0 for x to get one ordered pair, you put in a 0 for y to get the other ordered pair, you use what they call the intercept method. Okay. Those are both lines. Are lines functions? Yeah, they are. You know why that's a function? Y equals 5? You know why I can call that a function? That's a horizontal line. Oh, the headache that causes people. Because you see this y sometimes, you think y-axis, you think the y-axis is up and down, that's got to be a vertical line. It's not though. What it is it is a horizontal line that goes through 5 on the y-axis, but it's horizontal like that, and that's a function. So what are vertical lines? What are those? Those are the x equals. So if you ever see x equals a number, that's a vertical line and not a function. In fact, calling a vertical line a function is like pretty much the worst thing you can do, because it fails the vertical line test so badly that the vertical line hits the graph infinitely many times. Look at this. Let's see if it's a function or not. Ah! No, the vertical line hit it so many times, it's not a function at all. Horizontal lines, yes. Vertical lines, no. Remember that. Is every single line ever a function? No. Is every line ever except a vertical line a function? You bet it is. Sorry, I got scared of the vertical line. I apologize. All right, so what we need is we need tip-offs. We need clues. How can I tell, without graphing, if an equation represents a function? In other words, no repeated x values with different y values, and passes vertical line test. I want to know that. All right, everyone. All right, so you're going to be given an equation, maybe like that mess I put on the previous page, and someone's going to say to you, hey, is that a function or not? And you're going to be like, I don't want to graph that. I don't know if it passes the vertical line test. What gives? What can I do? Well, bring it on, because we have one big tip that really helps us with this. If you see y to an even power or a plus or minus, then it is not a function. And I say not a function with a grain of salt, because as you move your way through mathematics classes, and I hope you plan on taking a lot of math after this class, you might see some ways they can get around this by doing some restrictions and stuff like that. But for the most part, this is true, and this will definitely get you through this class. And as you become more mature in mathematics, you'll see what I mean when I say people might be able to mess with this. But if you ever see y to an even power or a plus minus, then it's not a function. That's the big thing. That's how we do it with equations. So it turns out most of the equations we look at are going to be functions. Otherwise, it probably is a function. So let's try our knowledge here. Y equals x to the fourth minus 3x cubed plus 2x minus 8. Yeah, I see an even power up there. I see an x to the fourth. Does anyone see an even power on a y? No. Does anyone see I know you see a minus sign here and a plus sign here, but does anyone see that plus minus symbol that's kind of stacked like that? No, it's not there. You know what this is right here, everyone? This is a function. No plus or minus, no y to an even power. This is a function right here. And what's especially cool about that is that means, everyone, that if I gave you an x value to plug in here, which we're not going to do right now because I don't feel like taking numbers to the fourth power and the third power, but if I gave you an x value to plug in there right now, everyone would get the same y value. There's no element in the domain that will give two different elements in the range. There's only one answer. That's what it means to be a function. So whatever the graph looks like, the graph passes the vertical line test. And every x value corresponds to one y value, and that's it. Oh, I love it. I love functions, and I love circles, but I also love functions. If this is critical to the example, let me make sure that's really clear. Does anyone see a y to an even power?
No.
I don't see a y to an even power. Does anyone see a plus or minus in there?
No.
What do you think this is?
Function.
That's a function. Oh, that's awesome to know that. That's awesome. Oh, how about this? Do you think that's a function?
No.
What do you see?
Y.
Y to an even power, y squared. That's not a function.
Circle.
It's actually a circle. Well played. We'll learn about circles. If you stick around long enough in this class, I'll teach you all about circles. Probably November. Huh? That doesn't get you excited about the class. Circles in November. Maybe you'll be better at drawing them than I am. Yep, that's a circle right there. Not a function. Fails the vertical line test. Still an important thing in mathematics. Here's another way I can demonstrate to you why this is not a function. Here's two ordered pairs that work in that equation. 0, 3, and 0, negative 3 both work in that equation. Because 0 squared plus 3 squared equals 9, and 0 squared plus negative 3 squared equals 9. Let's write a lot of Q's. Those are both true statements. Both those ordered pairs work. We have a repeated x value with two different y values, not a function. Fails the vertical line test. Hit, hit. Y squared. All works together. Not only that, but look at this. Anyone ever told you to do something like this in a math class? Get one of the letters all by itself? Check it out. If someone told me to get all the letters, the y all by itself here, what I'd do is I'd subtract x squared from both sides. And then many people, myself included, are guilty of often saying you take the square root of both sides, but that's not actually what you do. You actually apply the square root property. And if you apply the square root property, you put a square root over this side. But when you apply the square root property, does anyone remember what you have to put in front of that square root sign? A plus or minus. So basically that y to an even power and that plus or minus that I said were the danger signs, they're related. They're basically the same thing. That's not a function. Whether it's written like this or like this, it's not a function. So we really just need to remember y to an even power or a plus minus, but they're pretty much the same thing. Means not a function. Otherwise your equation probably is. Okay. Once you know an equation is a function and the equation is solved for y, and solve for y just means y by itself and no other y. So you have one y all by itself on one side of the equation and there's no other y's anywhere else. That means solve for y. So once you know something is a function and you solved it for y, you can demonstrate it's a function using function notation. And this is the part that I blinked, and I was confused for a long time because I didn't understand what had just happened. Because suddenly, one day, the teacher stopped writing this and started writing this. And I was like, what gives? What happened? What do you mean? What happened? But I understood the why. What happened here? Well, this f of x is basically still a y. In fact, some people even write this. You're not going to see this in this class very often at all. But some people write that. They like put the y in there also. And what they're saying is they're saying y is a function of x. Y is determined by x. Whatever x you put in, there's only one y you can get out. Parentheses usually mean multiplication. But in this class, when you see this, that's written aloud as f of x, not f times x. F of x is how you say that out loud. And that just means I know this is a function. How do I know this is a function? Because it's a line. It's not a vertical line, it's just another line, and that means it's a function automatically. I know that. I know all lines except vertical lines are functions. And y was all by itself, so I was allowed to use this function notation. We're going to explore that a little bit today and see why we might want to use that function notation. Why we would suddenly mess with people's heads and change the y to that f of x. That's an equation of a line. I recognize that as the equation of a line. So if it's a line, is it a function? Yeah, that's a function for sure. Is it solved for y? So I know it's a function, but not solved for y yet. So I guess what I'll have to do is I'll have to subtract the 3x from both sides. So it will disappear on the left side. There you go, little annotation for your notes. Subtract the 3x from both sides. And then when you divide by 2, do you divide just the -3, just the 12, or both of them? Both, all terms. All terms get divided by the 2. It's still the same equation, it's still the same line. It doesn't matter if you graph it like this or you graph it like this, you're going to get the exact same graph, and they're both going to pass the vertical line test. They're both going to be functions. The essential difference is what? This equation is what? It's solved for y. Y is all by itself on one side of the equation. So now what I can do is I can name it. No big mystery, everyone. The other one was called f of x. This is called g of x. Why do I do that? Because I'm working with two different equations. I have this equation up here and this equation down here. So I think I'll give them two different names. One of them is called f, one of them is called g. In fact, quite often we have to work with multiple equations, and the most used things you'll see are f of x, that's the big one, g of x, and sometimes when someone needs a third equation, they use h of x. You could actually use any letter you wanted, except you couldn't use the x again. You can't say x of x. But if you were really jazzed about this, yeah, you could say p of x. That's fine. In fact, sometimes people do that when the equation models something in a real-world situation. They take a letter over here that has to do with that. Like if someone's doing something about how much something will cost, they'll do c of x, or cost. But in general, you're going to see the f and the g most often, and sometimes h. All right. Look at this. This is good. Is this a function? Negative 900 x to the 5th plus 1.4 x to the 4th minus 1 over x squared plus the square root of x minus 1 million. Is that a function?
Yes.
How do you know that's so fast? I already called it f of x. Well done. I already called it f of x. That's my mistake. if I didn't call a function. Once someone uses this notation, they're promising it's a function. So if I use this on something that wasn't a function, it's not your problem, it's my problem. I made the error. So, that's all you had to look at. For those of you who are freaking out because you see the square root here, and you're like, wasn't there a problem with square root? No, only when there was a plus or minus in front of the square root did we have that problem before. This one's fine. This is a function, a horrible function. I have no idea how to graph this thing. I've never graphed a function like this before. I've been doing math for a while now. I'm not going to do that. But I know it's a function because I was already told it was a function. Plus, I see no y's to even powers. Here's a classic math question. We've all seen a question like this before. Someone gives us an equation with a y and an x in it. They ask what y is when x equals a certain number. We know what to do. Someone asks me that question. I do a little bit of work. Maybe I even do it in my head because I'm especially smart, but I'll show my work here. Teacher's job is to show their work. 10. Done. I hope it's 10. Yeah, it's 10. Not only did I just plug a number in and I got a number back out, but what I did was I just generated one of the infinitely many ordered pairs on this. How many ordered pairs could I make if I really wanted to? As many as I wanted, yeah. I could keep on doing it until I get sleepy. Infinite number of ordered pairs. With this equation right here, if we all plug a 3 in, will we all get 10?
Yes.
And no matter what number we plug in, will we all get the same number back out? I mean, I'm not saying if we all plug in a 10, we'll all get a 10. What I'm saying is there only one correct answer for every x value?
Yes.
Yes, there is. You know what that means? It's a function. Getting this ordered pair is not the thing that told me this is a function. Knowing this was a line told me it was a function. And I decided to call it f of x. Now, everyone, if you get this next thing wrong, you fail the entire class and you never get to come back. No, just kidding. But look at this. I'm going to make a point. The point I'm trying to make is this, everyone. If I said this to you, make sure you plug it into the right equation. Is there anything up there to indicate which equation I'm thinking is the right equation? No, there's nothing up there. I'm just asking you to plug a 2 in. I'm asking you what y is. There's 2 different equations. I want to give the right answer. All right. Well, how about this? Is it clear now which one I want you to plug the 2 into?
Yes.
Yes.
Yeah, because I used function notation, and I took the liberty of naming my functions 2 different names. I named my functions f and g. And then instead of just saying blindly, hey, everyone, plug a 2 in there and see what happens, I'm specifically telling you which one to plug a 2 into. Note how the x that was there has been replaced by a 2. That means your job is to replace the x in the equation with a 2. It's the exact same question as saying, what do you get when you plug in a 2? But I can write it much quicker, and I can specify which equation I mean if I'm working with several equations at the same time. It's very slick. And we win. We get the order pair 211. So that's another reason we might want to use function notation. We're going to work with functions in here a lot. And when there's several functions going on at the same time, it'd be kind of nice to know which one I'm talking about. That's why we don't always use f. I mean, if I'm just working with one equation at a time, I might use f a lot. But if I'm working with 2 equations, I'll use f and g. If I'm working with 3 at the same time, I'll use f, g, and h. You can keep adding as many as I want. So, we're going to be dealing with functions almost exclusively in this class until we get to the last unit. So, a lot of times we're just going to see the function notation given to us unless the point of the exercise is then asking you, is it a function or not? And lots of functions out there, lots of them, not all of them, but lots of them can pretty much handle any number you want to put into them. For instance, class, there is not a single mathematical number out there that I cannot multiply by 2 and then add the number 1 to. I can do that with any number I want. So, if someone said, give me a bunch of ordered pairs around that graph, I can just start writing whatever numbers I please in there, knowing full well that I know how to double those numbers, multiply by 2, and add 1 to them. And really what you're doing is you're respecting the function notation, and you're plugging each one of those into that function, wherever you see an x. So we're going to get 3, 7, 1, -7. How many ordered pairs could I make? As many as I want. But the question that's going to be important to us, because it's not always going to be the same answer to this question, is this. What is the domain? What am I allowed to plug in for x? Maybe I'm working with an equation where I can plug in anything I want for x. Can I plug a decimal or a fraction in here if I wanted? Yeah, no problem. I can do that. Plug anything I want in there. But there are other equations out there, good equations, functions, that cannot handle every number. If you don't understand what I'm about to say, don't worry about it, because we'll talk about it later in this course. If you do understand what I'm about to say, listen to this very carefully. If you've ever heard of something called imaginary numbers, they have nothing to do with domain. So you could have to pretend you don't know anything about them for this question here. Here's my question, everyone. Can we take the square root of a negative number?
No.
We cannot, no. Most calculators will give you an error if you try to do that. We cannot plug a negative number in there. So, can I plug any number I want into this function?
No.
No. How do you know it's a function, by the way?
That's the number.
Yeah, I told you it was. That's how you know it's a function. This is a function, everyone. But what I want to say is I want to say this. The domain for this one seems like it would be any positive number, but I might need a calculator, and 0. Can you take the square root of 0? Yeah, you can. 0 times 0 is 0. So you can plug a 0 in there. And some numbers I could plug in there, and you'd have a fine time of it. If I said, what is f of 9? The square root of 9 is 3. Not plus or minus 3, just 3. We'll talk more about that in this class later also. But the square root does just mean the positive root. So I can plug in any positive number I want. Now, am I allowed to plug a 2 in here, everyone? Mathematically, yes. But would most people reach for the calculator at that point and get a decimal approximation?
Yes.
Probably, but you're allowed to. So, nasty decimal, but it's okay. So it's a function, because I told you it was a function. I use function notation. And furthermore, I can plug in 0 or any positive number I want. That's the domain. Huh, all right. What about this guy up here? No matter how far you go in math, how many math classes you take, there's going to be a rule that sticks with you throughout the entire thing. And that is there's one number out there you are never allowed to divide by. You can never have this number on the bottom as the divisor. And what number is that?
0.
0. We can't put a 0 in there. I cannot put a 0. Now, I could sit here all day long plugging any number I want in here, and I would get answers as long as I don't plug in 0. It's a function. I'm promising it is a function. But what we want to say is we want to say domain is any number but 0. Does that sound okay to everyone?
Yes.
Any number but 0. All right. Now the problem is this is a math class. Well, actually that's the good thing. This is a math class. And that means they don't want these domains to be written like these sentences like that. That's a little bit clunky. If someone says, what's a domain? You don't want to have to say, well, the domain is any number but 0. And you don't want to have to say any positive number, but you can also use 0. It's a little bit of a mess. Even this would be a little bit better. Just simply saying people, x cannot be 0. That's pretty cool. But what we're going to learn is we're going to learn a more mathematical way to tell people the domain. How do we give domain? We describe what numbers from the real number line can be x values. We're going to learn something called interval notation. Interval notation will be with us for the rest of this class and many other math classes you might take. So you don't want to snooze through interval notation. It's a bit of a pain, so it's a very easy thing to think, you know what, I'm going to not pay attention to this and just ride it out and hope that doesn't come up. It comes up a lot. So stick with me here. In plain English, if you were just talking to someone on the street, if you were doing street math, and they asked, what can you plug in there for x? You could say anything you want. Here's the number line, everyone. What's all the way down to this end as far as you can go, and you can't even get there. It's so far down. Negative infinity. Negative infinity is not a number. You can't actually get to negative infinity. And what's all the way up the other way?
Positive infinity.
Positive infinity. Infinity, remember, is not a number. It's a mathematical concept. So if you're having a contest with a friend where you're seeing who can name the larger number, and you say 6 and they say infinity, you won because you actually named the number. So this goes forever in both directions. We want to say that it goes forever in both directions. We want to say any number, no matter how far you go this way or how far you go this way, works. So we write this. I know I'm using parentheses, everyone, but this is an interval, not an ordered pair. This is our mathematical way of interval notation of telling everyone you can pick any number you want anywhere on the number line. Some of you may have seen this before. It's kind of like a double R. It means all real numbers. That actually is a correct answer, but it's not the notation we use in this class. I'm not telling you this is wrong. I'm telling you that the math homework is not going to like it if you put that, because the math homework is going to say give your answer in what we call interval notation. So don't strike that from your memory forever, but it's not what we're going to use here. All right, we're back on the street. We're doing street math again. Someone says, can I plug a 0 in there? What do you say?
Yes.
Yeah. Can I plug any positive number I want in there?
Yes.
Yes. So we don't want to tell our friends on the street that they can plug anything they want in there. We want to tell them, you can plug in 0 if you want, or you can plug in any number you want that's bigger than 0, and that's going to be your domain. Well, I can't do this because that means anything goes. But what's the farthest left number we can use?
0.
0. Uh-oh. Other than just me putting a 0 instead of a negative infinity, what looks fishy there? That doesn't look like a parenthesis. It looks like I drew a bracket. That bracket's trying to tell you this. You could use 0. Bracket have 2 T's or 3? All right, that's what that means. It means this right here is exactly what we were saying out loud before. 0 and anything bigger than 0. That's what that means. That is called interval notation, everyone. That is the interval that means 0 and everything bigger than 0. How about this one? Now, did we agree before that it's pretty much correct just to tell someone don't put a 0 in there and you're cool? That's pretty much correct. Here's a very awkward way of saying that, which actually turns out is the secret to doing this problem. Now, that might be the wordiest way to say it, but that is accurate. If you want to plug something in there, you can plug anything less than 0 you want, or you can go ahead and plug in anything bigger than 0. And what number am I excluding by doing that? 0, but that's very cumbersome, but that is correct. Now, that looks a lot like what I wrote for the square root. It looks a little different. What looks different about that than the square root one?
No parenthesis.
No, it's a parenthesis, not a bracket. This parenthesis right here means close to 0 as you want, but not 0. That means you can plug in 0.1. You can plug in 0.01. You can plug in 0.0000001. You can get as close to 0 as you want, but are you allowed to plug in 0? No, that's why we use a parenthesis. The reason we have to use a parenthesis is because we can't put a 1 here because there's so many numbers between 0 and 1 that are okay to plug in. It's kind of like asking someone, what's the number between 8 and 9? Well, 8.5, but isn't also 8 3/4 in there also, and 8.2 and all those? And no matter how close you pick two numbers together, there's always an infinite number of numbers still in between them. You can get as close to 0 as you want, you just can't get to 0. Because if you put in a 0, you're going to divide by 0, and that's how you end the world mathematically. That's called a union symbol, everyone. It's not the lowercase u. It looks like a lowercase u, absolutely, but it's actually a little union symbol. It looks like a little smile. It means or. No, actually that means and. The intersection means or. That means you can pick any number from here, and you can pick any number from here. Any number except 0. Class, if you did not sign that attendance sheet, I need you to come up here at the end of class and at least tell me you were here, because I got to drop people from the class that don't come the first couple days. This is getting posted. Let me just do this here.